Welcome back, class. So, we did this chapter 13.1. We skipped 13.2. We did 13.3, taught us how to do partial derivatives and sort of taught us what they were. And then I got into 13.4, just started 13.4, which is some good word problems. I'm going to keep going here. 13.5 is kind of a funny little section. I'm going to skip it temporarily. Maybe I'll find something important to come back to. But 13.6 is my favorite, most important section. So maybe I'll get there today. Maybe I'll get started in there today and get a couple ideas going. But I thought I'd start with a little homework like in 13.3. I just saw this question. Let me try this. Yeah, I told you guys to do 49. I'm going to just try this 46. It's a little too easy looking. So I'm in 13.3. I just want to look at this 46, which says I have this function. It's the sine of xy. Oops. The sine of x times y. That's z equals the sine of x times y. This is a 3D function. And then they say I'm at this point, 2 comma pi over 4. I'm at this point 2 comma pi over 4. You know, what's funny is when they give me this point, they give me an x and a y value. You know, if you're really on this 3D surface, this is a three-dimensional surface, then, you know, there is a z value associated with this. Anyway, but they usually, when they give me this point, they're giving me sort of the point from the domain, which is the x and y value that you plug into the function. Apparently they don't think it's important to have the z value, and maybe it's not important to have the z value, but just for fun, this is a point on the surface, and I just want to, I'm just going to fill this in. What is the z value? And if you take the 2 and the pi over 4 and plug them in there, you end up with 2 times pi over 4. 2 times, that's pi over 2, and the sine of pi over 2 is 1. Good job. So anyway, there's where I am. I'm on this surface. There's a surface in space here, and I'm at this point on the x-axis, out 2, over pi over 4, and up 1. I'm standing on this surface. And now what they'd like is they'd like me to calculate the partial derivative with respect to x at this point. So the partial derivative with respect to x, oh, by the way, and the partial derivative with respect to y. So these aren't difficult. We've practiced this a little bit in the first couple days. I walk in here and I try to do the partial derivative with respect to x, which means I treat x like the variable and I treat y like a constant. So first off, though, I run into a sine function. The derivative of a sine function is a cosine of xy, and then the chain rule spits out the derivative of the xy with respect to x is a y. And then it might be better written out front because it's not part of this angle here. So maybe it's better written as y cosine xy. So that's cool. Now, similarly, let's do the derivative with respect to y. With respect to y, it's very similar because you run into the sine function and you get the cosine of xy. But then you spit out, the chain rule spits out an x this time, the constant x. Okay, which is x times cosine xy. Okay, so I do have these two different derivatives. When you evaluate them at this point, as you can see, we didn't need the z value. When you evaluate the derivatives, you just need the x and y values. That's why that was all that was given. So if we evaluate them at this point, the y value is pi over 4. Oh, shit. And this is going to be the cosine of 2 times pi over 4. And that's the cosine of pi over 2, and that is 0. That is 0. And now, I'm a little disappointed I did this problem. This one's going to be 0 too. There's nothing wrong with 0, but I was going to say something else. This is 2 times pi over 4. And the cosine of pi over 2 is 0. So this one happens to be 0. I mean, for a student who might be doing their first little work here, they might think, oh, these are always the same? Of course these are not always the same. This is just a coincidence here. I'm at a very special point here where the slope is 0. What we did last class was I told you what this meant. And I wrote down what it meant, and I'm not going to write it all again, and I described what it meant. So let me just describe it one more time. Again, we're on this 3D surface. We're at this point, out 2 on the x-axis, over pi over 4, up at this point 1. So we're standing at this point. And then here's the deal. The partial derivative with respect to x is the slope in this direction. And when I say this direction, what I mean is I'm pointing parallel to the positive x-axis. Anyway, what is the slope in that direction? 0 in this case, which means I'm kind of at a little level spot. You know, for fun, if you wanted to pretend that the slope was 3, I'm sorry it didn't come out, but if the slope was 3, that would mean it's rising in front of me. You know, it's 3. The slope is 3, which means if I took 1 step forward, I would have to take 3 steps up. The rise over run in this direction is a 3. It's not a 3, it's a 0. The partial derivative with respect to y is the slope in this direction, parallel to the y-axis. So that's what we're calculating when we calculate these 2 partial derivatives. We can get these, we're getting these 2 slopes. And they can be different. I mean, that could be 3 and this could be -7. I mean, this could be rising in this direction and falling in this direction. I mean, they can be all kinds of numbers. It's interesting and that these 2 happen to both come out to be 0. If this is 0 and this is 0, then we're at a kind of a special point. We're sort of at a max. We're sort of standing on top of a hill or sitting in the bottom of a valley here. With these slopes being 0. And that's a little preview of what's to come. We are going to look at maxes and mins and 3Ds. That they weren't after all that. They just wanted me to evaluate this. But the fact that they both came out to be 0 was just kind of an interesting, important place, actually. It's a max or a min. And it's kind of a coincidence. I could have any slope in that direction and any slope in that direction. They can definitely be different. I highlighted that I really love this 13.6, and the reason I love 13.6, and I hope maybe I'll get there today, but I'm sort of getting there now, and that is I can find the slope in any direction. It's called, we'll get there, but I can use a combination of these 2 slopes to find the slope in that direction, that direction, that direction. I can sit here and find the slope in any direction I want. But as of today, in 13.3, I got the slope in the x direction, and I got the slope in the y direction. That's kind of all I got. Yes?
If we, this is probably a total misunderstanding of the material here, but if we integrate the partial derivatives, would we get
the function?
Yeah.
Yeah, that's true, and that's important and necessary, but not much in this chapter. But for some later stuff, we will be trying to, we have the partial derivatives and we're trying to get back to the function, sure. That is an exercise in differential equations, and when we have these and we're trying to get back to the original function. But go ahead.
So if we just looked at the partial derivative in the x direction, would we be able to get an x component? Speaking like with vectors, would we be able to get an x component? Like, for example, when you had vector value functions, would we be able to get the x vector value function for that equation?
Yeah, you might be mixing contexts. I mean, for a little while here, I'm not talking vectors. I mean, there's no vectors here necessarily. I got a function. It's a scalar function. Its derivative is a scalar function. If you integrate with respect to x, You do get back to that. If you integrate him with respect to y, you do get back to that. But I don't think I need to mention vectors in this context. I wanted to do the slope at a point, and I wanted to do both slopes at a point, and I wanted them to come out to be different numbers, but this particular one were both zeros. But I wanted to see these two slopes. Let's see, what else can we do? That was 13.3. I assigned some stuff up in the 100s. I think I'll wait till y'all do that before there's a 113, a 116, a 117. None of that's too hard, but there's some good things to look at. When I move into 13.4, we did this Friday. We learned about something called the total differential in 13.4, the total differential. And I had a nice long lecture about what it meant, but I just want so I'm just going to remind you of the formula. It's the partial derivative of z with respect to x times straight up dx plus the partial derivative of z with respect to y times straight up dy. And I told the students Friday, I said, you know, this is called the total differential. It's sort of an approximation. It's an approximation for the actual change in z. The actual change in z is some change in z. This dz is an approximation for that. And it's called the total differential, and you could think of it sort of as, if these dx's cancel, then there's a partial change in z. And if these dy's cancel, you have a partial change in z. And the two partial changes in z added together is your total differential. You can sort of think of these as canceling, and you have a partial differential of z, a partial differential of z added together, you got the total differential of z. We did a problem or two, but the application of this turns out to be dealing with error analysis. So let me try a problem here in 13.4. 13.4. All right. I hate to do all your fun stuff here, but all right, I'll try this number 30. So I'm grabbing a problem in 13.4, and it's a little word problem, and it's number 30, and it involves error analysis. So let's see what happens here. Number 30 says, the possible error involved in measuring each dimension of a right circular cylinder is plus or minus 0.05 centimeters. The radius is 3 centimeters and the height is 10 centimeters. Approximate the propagated error and the relative error in the calculated volume of the cylinder. Wow, okay. Okay, we're talking about a cylinder, a right circular cylinder. They said that I can measure the height h. They also said I could measure the radius r. They said that when I measure those, I have an error in those. They said, when I measure each dimension of the cylinder, I get an error of plus or minus 0.05 centimeters. So here's what that is. Again, I threw this formula up here. Now I adapted to these error word problems. And the error in measuring h, we refer to as dh. And it's plus or minus 0.05 is what I just read, centimeters. The error in measuring r is called dr. And it's plus or minus 0.05 centimeters also. That's what I just read. When I actually measured h and r, I got h was 10 centimeters, I think they said, and r was 3 centimeters. Let me just double check that. Yes. And then here's what they want. Approximate the propagated error and the relative error in calculating the volume of the cylinder. So you know that that's how this stuff works. If I want to calculate the volume of this cylinder, volume of a cylinder is pi r squared h. But if there's some error involved in the radius and there's some error involved in the height, then there will be, that error sort of compounds itself and there will be error involved in the volume. And we use the total differential to approximate that error. You know, maybe this is the real error and we're using the total differential to approximate the actual error. So we're using this. Now, except I'm using this with these letters. In other words, I think who's playing the role of my z here? That's v. Who's playing the role of x's and y's? I believe that's r and h. And I'm going to find dv. dv is the error in measuring the volume. This is the error. Well, yeah. When I read the error for h, I called it dh. When I read the error for r, I called it dr. The error for the volume is dv. And so I'm going to use this formula. This is the error in calculating the volume, and the formula is this formula, this differential. You know what I'm going to do? I'm going to write it. Except I'm going to write it in these letters. I'm going to write, what am I doing? I'm doing the partial derivative of v with respect to one of the variables, r times dr, plus the partial derivative of v with respect to the other variable times the dh for that variable. Okay, now let's actually do it. Let's see. What is the partial derivative of v with respect to r? The partial derivative of v with respect to r.
2 pi r h dr.
Because you're going to treat h like a constant, and so you're going to treat r like the variable, and you're just going to go 2 pi r h. Yeah, 2 pi r and h. I mean, I treated the pi and the h like constants, and I did the 2 right. Cool, that's dv dr times dr plus, now we need dv dh. Treat h like the variable, treat r like a constant, and his derivative is
pi r squared.
Pi r squared. Good, thank you. Pi r squared times dh. So there you go. This is the total differential, is what you call this. This is the error for the volume. All I got to do is fill in my r and h and my dr and my dh. The r and h were the measured values of r and h. The dr and dh were the errors when we measured those. You know, when I fill these in, technically there's like a little plus and minus in there, and there's also a little plus and minus in there. But what I kind of like to do is just factor the plus and minus all the way out. So I think I'll just factor a plus or minus out front and then sort of fill all this in. It's 2 pi, the r is a 3, the h is a 10, the dr is a 0.05. Right, plus, this is a pi, this is my r squared, and then my dh is a 0.05. Okay, that's it. I'm down here at the bottom of the board. This is dv. It's going to have this plus and minus in front of it. I'll just move up here. Have you done it yet?
Yeah. 10.84 centimeters cubed.
That's your final answer. You got the pi worked in there and everything.
Yep. Let's see.
Okay.
Yep. 2 pi, or 2 pi times 3 times 10 times 0.05 plus pi times 9 times 0.05.
Okay, so I'm getting plus or minus 3.45 pi, but let's go ahead and multiply the pi. And so what is 3.45 times pi? Probably what you said. You said 10.84.
Exactly.
Yeah, plus or minus 10.84. The units are
Centimeters cubed.
Centimeters cubed, because this is some kind of volume. I didn't really keep track of my units, but that was centimeters, that was centimeters, that was centimeters. These are centimeters cubed. That was centimeters squared, centimeters, yeah, it was centimeters cubed. Of course it was, but sometimes it's cool to double check that. Yep, cool, that's the error. But you know what, again, it's an approximation for the error. We use this, the question said approximate the error using the total differential. And that's what we're doing. It's easy. I mean, it's kind of cool. It's kind of fun. It's this formula. The other day I did one of these with 3 variables because it had 3, well, hang on. There are 3 variables here. There's V, R, and H, but remember, V is really a function of 2 variables. The other day I did one where this Z was a function of 3 variables. And so when it is, there's just a third thing here, dz dt times dt. You know, there's just you just extend this formula. It's given like this, but it can extend into multi-variables. Yes.
What is the error in the approximation?
Right. Well, good question. I mean, I almost don't care. For very small changes in H and changes in R like this is a good approximation for the error. I could show you something, but hang on a second. The other thing they wanted, so this is called the error. They also wanted what's called relative error. They asked for relative error. And relative error, and again, maybe you know these from your science classes and stuff because you do lab work and you work on error sometimes. But relative error is this. It's dV over V. It's like a measurement of how much, is this a lot of error or is this a little error? Well, it sort of depends. It's 10.84 centimeters cubed worth of error out of how much was the actual volume. I never did calculate the actual volume, but with that R and that H, the volume is pi times R squared H, 90 pi.
282.74.
282.74 centimeters cubed. So that's the actual measured volume. And when you put dV over V, and divide this, what's kind of cool is the actual units cancel, and you just get like a decimal. What is this decimal?
10.84 divided by 282.74 is 0.038.
Thank you. 0.038. We can call that a relative error. If you multiply it by 100, it's 3.8%. Maybe you call that a percentage error. I don't think, to me it's still relative error. I mean, that's what it is, but you either write it as a decimal or a percent, I suppose. We tend to like to make it a percent. So technically, relative error is percentage error multiplied by 100, or the other way around. Multiply 100 times your relative error, you got percentage error. But I call them the same thing. But neither one of them are error. Error is the actual error, or the calculated error, and then this is a percentage error, which helps me. I mean, whatever. That's not that bad of error, I guess. 10 or 20% is pretty bad error. 3.8% isn't too bad. Yeah, we use this total differential to calculate this error. If you really want to do error, how do you really do error? I mean, if you don't want to use calculus and you don't want to approximate, like if you want to find actual error, we did a little of that last class. I think what you kind of have to do is do this. This volume was measured to be 282.74 centimeters cubed. and that was using the measured values of h and r. Well, what if they were off a little bit? Like, what if they were off on the plus side, 0.05 and 0.05? So in other words, what if this was pi r squared, but that's 3.05 squared, and h is 10.05. You with me?
Yeah.
I mean, if they're off by plus, if they were both off by plus 0.05, then you could get a different volume. And what would it be? And so this is kind of just a lot of calculator work here. 3.05 squared.
$293.71. Right? Wow.
293.71, 293.71, and so the difference there is about 11, or almost 11, 10.97, right?
Yeah.
See, so that's the error, that's one error that we calculated, actual error. Now look at our error, using the dV, which is an approximation to the actual delta Z. You know, we're pretty damn close. That's why we're happy using this. But you know, you could have, what if it was on the underside? What if it was 2.95 squared and 9.95? In other words, it was plus or minus 0.05. So what if they were both on the minus side? Then you get whatever. Yeah, I mean, you could play this game forever.
What if it was a foot off?
Right.
That'd be some serious error.
272.03. So how is that? What's that difference? That's 10.71, huh? Huh.
I bet if you average them.
And if you average those, you might really get this, I'm telling you. Yeah, you would.
Yep. Exactly.
What if, I mean, there's a lot of scenarios. What if one of them was off by the plus? Like, what if this was the 3.05 squared and then the other one was off by the minus? You know what I mean? He's off by the plus 0.05, but he's off by the minus 0.05. I mean, then you could have the other scenario is, okay, he's off by the minus 0.05 and then he's off by the positive 0.05. I mean, there's a lot of different scenarios that happens with this error.
Get about. Actually, get way lower.
290.79, 290.79. Right, see, right, when they were both at their extreme, that gave me the most error. I got you. Right? Extreme on the high end or both extreme on the low end. Maybe it depends on the problem, but extreme on the high end, extreme on the low end, a little bit high and a little bit low, it lands somewhere in the middle. Right? Right?
Yep.
Same with this one, I guess. Huh. But, again, I'm sort of just doing this for fun. Analyzing the hell out of all these errors. This is what we're trying to do this. We stop here. We use the total differential. It's a good enough approximation. It's good enough. I want to do another one. There's a lot of good ones. That was kind of easy and basic. Check out this. I'm going to do this 34 in the book. Here's another one. 34. I'll just erase all this. In 13.4, number 34 is another good question about error. Let's see what it says. Then centripetal acceleration of a particle moving in a circle. The centripetal acceleration of a particle moving in a circle is A equals V squared over R. A is the acceleration, it equals V v squared over r, and v is the velocity, r is the radius of the circle. Approximate the maximum percent error in measuring the acceleration due to errors of 3% in v and 2% in r. So they just told me that the error in v was 3%. Hang on. The error in v is 3%. Now, I want you to, and they also, okay, now watch, I want you to listen close here. So the error in v is 3%. So you might be tempted, like the last problem, to write down, oh, so the error for v is 3%. There's a problem with that. There's a big problem with that. When they give you a percentage error is not dv. A percentage error is, and this was volume from the last problem, but this is velocity. But anyway, an error is dv. A percentage error is a relative error. It's dv over v. So when you read this problem and you see a percent, this is not dv. I'm wrong here. It's dv over v. It's 0.03. They also said the error in measuring the radius. They said the error in r is 2%. Anyway, you might be tempted to say, oh, cool, man, the error, dr, is 2%. No, it's not. It's dr over r that's 2%. So this was what was given. The formula was given. And I think what they're asking for, what did they ask for?
Max percent error.
They asked for percent error, and they asked for max percent error, which I think I need to discuss, but hold on, we'll just skip. They asked for the percent error in the acceleration. So look, like this one said, calculate the error in the volume. So they wanted this. But they also said relative error. They wanted both. This one didn't say both. This one said percent error in A. So they're not really asking for dA. They're really asking for dA over A. I mean, that's percent error. That's what they're asking for. Well, okay, I got my work cut out for me. Let me get rid of this. Let me get rid of this stuff here. I got a little cool, tricky way to do this problem, so I want to show you. That's why I did it. That's why I want to show you something here. But I've read it and outlined it real well. I think that's important. Read it and outline what was given and what's being asked for. But then, ultimately, though, I think I want dA over A. Let me just start by trying to get dA. And then if I want dA, then what I need is the partial derivative of A with respect to, well, hang on, I'll write it in here. We need dA dV times straight up dV, and we also are going to need dA dr times straight up dr. That's what this is. I wonder what is dA dV? What is dA dV? The derivative of this thing with respect to v. That means treat r like a constant. Take the derivative with respect to v. Just 2v over r. Just 2v over r. That's cool. We need that right here. I also need dA over dr. I need dA dr. In other words, treat r like the variable. You treat v squared like a constant. So r is the variable. Move it up. Call it r to the negative 1. Take the derivative. Negative v squared r to the negative 2, or negative v squared over r squared.
Yep.
Cool. Cool. R is the variable, move it up, r to the negative 1, do a derivative.
So, quick question.
All right, go ahead.
Is that parentheses negative v n parentheses squared, or v squared times negative 1?
Yeah, that's v squared times negative 1.
Okay.
The negative is not being squared. Okay, here I go. I'm going to fill this stuff in. What dA dV? dA dV is 2v over r. Okay. dV is just something. dA dr is this negative v squared over r squared times dr. All right, so you gotta watch out for my V's and R's. They start to look the same. Be careful. All right, well, okay, so last time I had a V and an R and a DV and a DR, and I just filled them all in and calculated the answer. You know, this time nobody gave me a V or an R, and they didn't really give me a DV or DR. They gave me these percent errors. Now I can figure out how to use those, and I can do a lot of different ways to use those, but I want to show you this cool trick. Ultimately, they wanted dA over A. So if I divide this side by A, then I'll have dA over A. Well, that means I got to divide this by A, and I got to divide this by A. But I'm going to do that, but I'm going to do it in the form of what is A? Hang on, what is A? There it is. It's V squared over R. So I divided this by A, I divided this by A, and I divided this by A. So this is my nasty, huge, terrible formula. And if I had V's and R's and stuff, I could fill this in. But let me clean it up. Watch the beauty of this. Watch the beauty of this. If you flip this up here, it's an R over V squared. The R's cancel. One of the V's cancel. And I'm left with a 2 times dV over V. What about over here? If you flip this up, you're flipping up this R over V squared. R over V squared. Well, the V squareds cancel. One of the R's cancels. And you're left with -1 dr over R. And guess what? You were given dV over V. You were given dr over R. They're right there. That's your 0.03 and your 0.02. You fill them in and you're done.
So 4% error?
Well, let's see. So dA over A is 2 times the dV over V. All right, which is a 0.03. And then -1 times the dr over R, which is the 0.02. And so that's a 0.06 minus a 0.02, so that's a 0.04, or you could call that a 4% error. All right, hang on. That's good. We're doing good, except for one problem. They did ask for maximum percent error. They asked for percent error. I've tried to focus on that, but they used this word maximum. And I tell you, there was a time when that used to confuse me a little bit, but I've got it figured out now. Here's what they want. They weren't even that clear, but it's true. When you have these errors and they're percent errors like this, it sort of depends on how they're worded. But this error of 0.03 could be on the plus or the minus side. I mean, they didn't tell me plus or minus, but I should assume. A 3% error, I don't know if it's on the plus side or the minus side of the measured value. So this is plus or minus, and this is plus or minus. And when you ask to find the maximum error, what you're supposed to do is analyze all the different plus-minus scenarios. So now, by plugging those in, what I just did was when they were both plus. Let's do it if they're both minus. If they're both minus, he's a negative 0.03. This has a minus sign in it, and this is a negative 0.02. Let's see what we get now. Now we get negative 0.06 plus 0.02. Oh, and now I get negative 0.04. All right, well, that doesn't matter then. Okay, so both of these ended up with a plus or minus 4% error. Huh. But you see what I'm doing? I'm analyzing the two pluses, then I'm analyzing the two minuses. Is that what I did? Maybe I should check out the plus and then the minus, or then the minus and then the plus.
If the second one is minus or vice versa,
right,
that's going to be bigger.
Right, so here we go. So 2 times, let's see, if this first one's plus 0.03, then a -1, and then the second one's a minus 0.02. That's my plus minus situation. Yes, it is. That's a 0.06 plus a 0.02. That's a 0.08, a positive 0.08. What if we analyze it with a negative here and a positive here? Then he's negative and he's negative, then that's negative 0.08. So both of these lead to the 8% error. So it's not 4. The answer is, the maximum error is which one gives you the most. When you analyze all 4 scenarios, all 4 of the plus minus scenarios, or maybe there's more than 4 if there's more variables, but if you analyze all the plus and minus scenarios, find the biggest, then there's the maximum error, 8%. So it's okay, it's kind of cool. It's different than the last problem. The last problem, I don't know, they didn't say maximum, but I don't know if I think we found the maximum. I don't think it mattered. This was cool though. This was a bunch of percentages. I had to know what I was doing. I had to read carefully and know what I was doing. And then the way it fell out was very cool. It came out pretty darn easy. But to do maximum, analyze all the scenarios. Analyze all the scenarios. That's enough of these for today. There's more of these in 13.4 homework. Error analysis. They're good to practice. Using the total differential to do an error analysis. But I'm going to do this. I'm going to get into this 13.6 now. Again, I skipped 13.5. I skipped 13.2. This 13.1 and 13.3, we spent a couple days there, but I moved quickly into this good stuff, and now I'm into the really good stuff here. 13.6. Let's show you. Let's do this. So there's several kind of big ideas here, but let's just start with the first one. The first one is called the directional derivative. Directional derivative. That's the name of it. It has this notation. D, capital D, with a subscript unit vector u, f of x, y. The formula for that then is this. It's the partial derivative with respect to x at the point x, y, times the unit vector, the u1, which is the x component of the unit vector, plus the partial derivative with respect to y of the function times the u2, the unit vector, the second component of the unit vector, or the component of the unit vector in the y direction. Sometimes I just call that the duff. It's the duff. It's the directional derivative. What the hell is it? I'll tell you what it is. It's the slope of the surface. It's the slope of the 3D surface. It's the slope of the surface, f of x, y, that's the function. It's the slope of that surface in the direction of the unit vector u, which is a little unit vector u1, comma u2. So I previewed this 45 minutes ago or so when class started. I mean, this is big. This is a big deal. So 45 minutes ago when this class started, I said, okay, in 13.3 we learned how to do partial derivatives. What do they mean? And what I said was the partial derivative with respect to x is the slope, you're standing on a surface, you're at a point, and if you want to know the slope in that direction, which is parallel to the positive x-axis, and by the way, you're really looking in that direction. If you calculate the partial derivative with respect to x at this point, maybe the answer is 4, and the slope in that direction is 4. By the way, if I turn around and look behind me, that means it's rising 4. If I turn around and look behind me, the slope is -4. And that's kind of a new concept in this Cal 3. I mean, back in Cal 1, a slope was a slope. There wasn't 2 slopes or 15 slopes or... Right. I mean, there was a... But now, it does matter which way I'm looking. If I'm looking this direction, the slope is 4. At this point, if I turn around and look behind me, though, it's -4. I mean, it's at this instant, by the way. If I take a couple steps this way, everything changes. Or move to some new point, everything changes. It's always it's instantaneous. Anyway, the partial derivative with respect to x is this slope. The partial derivative with respect to y is this slope. And now this new thing is sort of an average of these two, or some sort of average of these two. As you can sort of tell, the formula has these two things in it. This new thing, duff, though, is the slope in any direction. The only thing you got to give me is some unit vector that points me in that direction. So then you can think of it like this. If you give me a unit vector that points me in this direction, then you can think of this formula as, this is the slope in the x direction multiplied by how much you're, how much you're looking in the x direction. This is the slope in the y direction multiplied by how much you're looking in the y direction. And then you kind of add those together to get a sort of an average or a slope in this direction. A slope in the direction of the unit vector u. So now I'm standing at a point on a surface, man, I can tell you the slope in any damn direction you want. Any direction you want. You know, if you're given an angle, then this unit vector looks a little different sometimes. If you're given an angle, this is a unit vector. Cosine theta, sine theta is your unit vector. And so I've seen this formula written differently. I've seen them put cos theta and sine theta right here, which is what they are if you have an angle. If you have an angle, that's what these are. Yeah, man, the duff, the slope. It's the slope of the surface in any direction. It's funny though, you gotta give me a lot of things, man. To calculate a slope, you gotta give me a surface. You gotta give me a point to stand on that surface. And then still not enough, because I still don't know, okay, now you gave me a surface and a point, but I still don't know which direction you want the slope in. You give me a unit vector, points me in a certain direction, I can calculate the slope in that direction.
What if you had a unit vector whose value was dependent on the on where you were in the 3D surface?
I don't know. See, this unit vector is just a direction to look in. Look, they might say, look in the direction 2, 5. Okay, I know how to do that. That's out 2 and over 5. Okay, that's that direction. Look in the direction, oh, but it's not a unit vector. It's 2, 5. So for the purposes of the calculations, I need to make it a unit vector. But making it a unit vector will just shorten up the length of that vector. I'm still looking in that direction, you know. But you can tell me to look in any direction. Just look in the direction -7, 3. Okay, the direction -7, 3 is, I'm turning around because it's -7 on the x-axis and 3 on the y-axis. So it's -7 on the x, 3 on the y, it's that way. I'm standing on the surface, maybe I'm here, but I'm looking that way and I can calculate the slope. It's going to be a number, it's going to be like 12. Holy shit, it's steep. Or it's going to be -20. Holy shit, it's steep. I mean, or it's 0, or it's, you know, it's some number, some slope in that direction. Then move and point in this direction, it's a new slope. Move and point in this direction, it's a new slope. You know, we're on this 3D surface, but this unit vector is just a 2D vector. This unit vector ain't pointing up or down. This unit vector is just telling me which direction to look in. It's a 2D vector. I'm standing on a 3D surface, and I'm looking in some direction parallel to the XY plane. That's what that is, and then I can calculate the slope in that direction. I can calculate the slope of the surface in that direction. Yes?
What if the unit vector given was cos x sine y? Which is the unit vector? It's divided by the square root of 1.
So the unit vector is a 2D vector, and when I said I'm giving you this, what I'm doing is I'm giving you this angle theta, and theta is good old measured in standard position, you know. So this is my unit vector u. So I don't know, man. You're confusing me when you say cos x sine y. I'm not sure. That means you're giving me two different angles. One of them's x, one of them's y. Yeah, I think we're off. We're not really. I don't know.
Well, I mean, if where you're looking depends on where you're standing.
Well, maybe you could make up a function that. Here's the thing. I mean, I don't know. What kind of slope do you want to calculate? This is a 3D surface. So first of all, you got to decide what point do you want to calculate the slope at. Then you go stand at that point. Then there's still an infinite, so there's infinite number of points to choose from, first of all. So you pick a point to stand at, and now you want to calculate the slope. Well, now there's infinite number of slopes to pick from too. You want to do this one, you want to do this one. Which slope do you all want to do? So I'm saying, given a direction to look in and given a point to stand on, there's your formula for the slope. Let's keep talking. So that's an important idea. We should do some problems, but it's just this formula. It's not all that horrible, but there's another one here. There's another big idea. The other big idea is this thing. It's called del f of xy. And this is a vector. So I'm going to put a vector symbol on top of it. And it's a two-dimensional vector. It's what it is it's the partial derivative with respect to x as the x component, and the partial derivative with respect to y as the y component. This thing is called the gradient of f. It's called the gradient of f. And we kind of loosely associate the word gradient with slope. Gradient is a slope, but I don't really like to call this a slope because it's a vector. It's not a slope. I mean, that's a slope. That's a number. In the end, that's a number, 12, when it's all calculated out. This is a vector. So I'm going to tell you what it is. It's called the gradient, but here's what it is. It's a vector. This is what the gradient is. It's a vector that points in the direction of maximum slope. So again, here we are, sort of talking theoretically again. But like I said, you give me a surface, which is a function, then you give me a point to stand on, and then you ask me which slope do you want me to do? This direction. Now you give me I got all these directions I can choose from, and I can calculate the slope. But anyway, guess what? One of those directions points is the direction of the steepest slope. I mean, when I calculate all these slopes, maybe this slope is 10, this slope is 13, this slope is 5, this slope is 2, this slope is -4, this slope is -8, this slope is -6. I mean, there's all these slopes as you go around and look. The gradient is a vector that points you in the direction of the steepest slope. It's cool, it's interesting. I don't know what the proof of that is, but that's what it is. And then, the magnitude of the gradient, which is the length of that vector or the magnitude of that vector, is the max slope. This is the maximum slope. Just to finish a few notes here, if the gradient points in the direction of the maximum slope, then right behind me, if that's the steepest slope, like I said a few minutes ago, if this slope was 4, if I look behind me, it's -4. So if this slope is the steepest slope, if this slope is 36, then right behind me, the slope is -36. And it's the minimum slope. So check this out. The negative of the gradient vector, the opposite of the gradient vector is negative. I won't even write what it is. It's the negative of the gradient vector. It points in the direction of minimum slope. Now his magnitude will be the same as his magnitude though. I mean, magnitudes are always positive. So, I mean, again, if the gradient points me in this direction, that's the direction of maximum slope. If you calculate its magnitude, you get 36 or whatever you get. Wow, that's the slope, 36. The opposite of him points in this direction, and what's the slope in this direction? If I said this is 36, what's this behind me?
36.
No, it's -36. Well, its magnitude, right? His magnitude would be 36, but the minimum slope is not 36. It would be -36. So watch what I have to say. I have to say the negative of the magnitude is the minimum slope. Sorry. Is the minimum. It's weird, dude. It's two things. The gradient is a vector that points you in the direction of maximum slope, but he ain't maximum slope. His magnitude is. Which is, there is a difference between a vector and his magnitude, but sometimes it's subtle. I mean, in math classes, I don't make it subtle. It's different. That's a vector. That's his magnitude. Sometimes in some classes, that gets blurred a little, right? Is it the vector or is it his magnitude? Cool. These are good notes. This is all 13.6. We should do some problems. There's actually one more good idea. I might just try one of my famous problems here. Here's one of my problems. I'm making up a function. 4x squared y minus 3xy plus 2y squared minus x plus 8 at the point 2, -1, -2, I think. So I think if you plug in that x and y, you would get that z. That's why I just put that in there quick. But this is me, dude. This is some surface, man. Some beautiful undulating 3D surface. And we are standing at this point, and what do I want to know? I want to know, find the slope of the surface. Or I could just say find the slope in the direction of the vector phi 3. Here's another question. Find the slope in the direction of theta equals 120 degrees. Yeah, I could add a little more to that. Let's see what happens.
Just went over an hour, by the way.
Oh, did I?